Hello everyone, and welcome back to another lesson in our Algebra 2 course. This lesson, Lesson 2, is about simplifying expressions and sets of real numbers. I want to start with a discussion of the different sets of real numbers. So following along in your notebook, which if you don't have it can be downloaded from my webpage, we're on example 2.1. And I've just copied it over here to the Paint application. So this is the real number set. And I want to start with the most specific one right here, natural numbers. And then we're going to build out from there and introduce more and more numbers. So what are natural numbers? You may have heard them called the counting numbers because we count with them. They start at 1 and they count up 1, 2, 3, etc. It's the first numbers most any human being learns. So they have a lowest number 1, and then they have no highest number, and you count all the whole numbers up from it. Okay, there is a special symbol for the natural numbers, and it is this double strike in. It just looks like someone typed an in with a typewriter and then hit it again, so it's just kind of extra big. All right, next we move on to the whole number set. And the whole numbers are the natural numbers plus one more number, the number 0. So technically when we talk about whole numbers, we can't have any negatives, but we can have 0. You'll notice there is no double strike symbol for whole numbers. They're just not that common a set to work with. We're more often going to work with either the integers or the natural numbers, but occasionally we'll deal with whole. Okay, now we're on to integers. To go from 0, 1, 2, 3, 4, 5, 6, 7, etc., to including all the integers, we need to include the negative numbers as well. So -1, -2, -3, etc. So what you can see is that a good way to define integers is numbers that have no fractional part. A lot of people say an integer is a whole number. As you can see, technically, they're the whole numbers and the negatives of the whole numbers. But just a good definition is numbers with no fractional part. All right, rational numbers. Now we're ready to add to this rational numbers. Well, rational numbers are numbers that can be placed in a ratio. And notice that each one of these subsets is inside the other. So the integers includes the whole, which also includes the natural. And the rational includes all the integers. And I want to make sure you understand why. Because if I had the number, say, 4, well, that's a natural number. It's definitely a whole number, and it's an integer. Well, how is it also rational? Well, I can express it as a fraction. That's what makes it a rational. I can express it as a ratio of two integers, 4 to 1. That's what makes it rational. But I don't want to confuse everybody with that, so I'll just take that off. But that's why the rational numbers include all those other numbers. All right, so let's talk about it. We can't very easily, we can kind of make a pattern to count up, but we really just need to pick specific ones to include. So 1/2 and 3/4, these are just kind of classic fractions. But once we allow the numerator to be bigger than the denominator, then we really get into rational numbers. And we can have negative fractions like -2/3. But we could also have decimals that can be converted to a fraction. So 0.25, that number is 1/4, so it's a rational number. Also, 0.3 repeating. You may have seen that like 0.3 with a bar. Well, that's 1/3. So it turns out that any decimal that it terminates or has a repeating pattern, there's a rule we can convert it to a fraction. So you may be wondering, well, then what kind of numbers would these be? Irrational numbers. Irrational numbers are numbers that cannot be put into a ratio of integers. You get it? They're irrational. Ir meaning not rational. So probably the most well-known irrational number is pi. In this course, you'll learn about another equally important irrational number called e. And it turns out that if we have a square root of something that's not a perfect square, that's also irrational. Say the square root of 3. The square root of 4 That's rational. It's just 2. But the square root of 3 is in between. And that's the thing about irrational numbers. They have this infinite in-betweenness that we can keep getting closer and closer to them, but they don't have some set pattern to their decimal. All right, so that's pretty much all the real number sets. And if we include all of them together, we make the double strike R, the real numbers, which will be the most common set that we'll deal with. Okay, so for practice, what I'd like you to do is I would like for you now to pause the video, and I want you to label the most specific set that you can for each number that it belongs to. So for example, if you had the number 4, we could certainly call that a real number or an integer, but I'd like you to call it a natural number since that's the most specific set that it belongs to. Okay, at this time pause the video and then we'll go over our work. All right, let's see how you did. 3/7. The number 3/7 is a rational number. So maybe you wrote out the word rational, or you tried to make the little double strike Q. I'd like you to know both words. Know the word rational and know the double strike Q symbol. Because as we go on, I'm going to rely more and more on those special symbols when they exist. 7.8. Well, this is a decimal that terminates. So it must be able to be put into a fraction. The way that I would do that is I would just move this decimal to the right one and then divide by 10. 78/10. We could then reduce it, but you can already see that I was able to express it as a ratio of 2 integers. So this is a rational number. -5 is an integer, which is the double strike in. And I'll just remind us that those are double strike in is integer. 1, 2, 3, 4, 5 is a natural number. So the double strike in, and I'll write that one out as well. Natural number. By the way, you might be wondering where they get some of these letters for the double strike symbol. Q for quotient, R for real, N for natural, but the Z, well, that's a little confusing, but it comes from the fact that these number sets were kind of laid down by a German mathematician, and Z is the first letter of a word in German that basically means integer. Okay, the square root of 20, we have to think, is that a perfect square? Well, the square root of 16 is 4, and the square root of 25 is 5, so the square root of 20 is like infinitely in between. You can keep picking different numbers and it's more in between. So this is irrational. Irrational. Pi is irrational as well. You may know some of the digits of pi, right? 3.1415926. And it just keeps going. And we can keep getting more and more precise, but the more digits I add, the closer I'll be around it. But I'll always be a little bit above or a little bit below the true value pi. Okay, the number 0 is a whole number. It's an integer, but it's not a natural number, it's a whole number. Okay, and I threw us a bit of a curveball here because you might think that this number here makes no pattern. 142857, 142857. Can you see that the pattern is repeating? And that is a very famous fraction. It is 1/7. It's famous for many reasons, and it's called the Phoenix number. And I think I'll save to describe what the Phoenix number is till a later date. But if you're interested, check it out. All right, for the next practice set, I want you to describe in increasing wideness the sets that each one of these numbers belong to. So if I give you the number 1, you would start with the fact that that's a natural number. But then you would get wider and say that's also a whole number, which is also an integer, which is also a rational, which is also a real. So pause the video, give it a try, and we'll go over your work. All right, let's see how you did. -4 is an integer. Oh, gotta go to brush mode here. So I'll use the double strike in. It's also a rational number, so I'll use the double strike Q. It's also a real number, I'll use the double strike R. Integer, rational, real. Okay, this is a natural number. It's a whole number. It is an integer. It is definitely rational. It is a real. The square root of 3. The square root of 3 is a decimal with no pattern. It's because it's not a perfect square. So this number is irrational. And it is real. All right, hopefully I had some success there. Let's take a look at our next problems. Okay, we have some examples to do here together, so let's get started with that. We're going to state which algebraic property was used to transform the expression on the left into the expression on the right. We can choose from associative, commutative, or distributive. Okay, let's see what let's define each one of these words first. What does the word associative mean? Well, I always remember this word by thinking about associates. I work with different people and they're my associates. They're the group that I'm around. I also have other associates that are my friends. But whatever it is, your associates, who you associate with, are your group. So when you think of the associative property, I want you to think about groups. The word commutative always makes me think about commute. When I lived in Austin and taught in Austin, I had an hour-long commute to work. That's how long it takes me to go from my home to where I worked. So commute is to move. So I want you to be thinking about moving. And then the distributive property always makes me think of passing out papers in class. I'm giving a little bit to everybody. So I want you to think, just like the word says, of distributing, giving, okay? So that's just kind of the kind of way I want you to try and remember, or at least that's how I remember it. Okay, let's start with the first one. 7 plus 9 is equal to 9 plus 7. Can we confirm that this is true? Well, 7 plus 9 is 16. And 9 plus 7 is also 16. So this is true. We can change the order in addition. So what I've done is I've moved the 7 to where the 9 was, and the 9 was to the 7. What did we say about moving? Commutative. So this is the commutative. Now, if I want to give its full name, this is what we call the commutative property of addition. And it is a good idea to say of addition because not every operator has a commutative property. The addition operator does, but the subtraction operator doesn't. You know, if I change the order, it changes the answer. So we need to realize the commutative property exists for addition and multiplication. So it's a good idea to list which one you're using. Okay, 4 times 2 times 3. These parentheses are grouping symbols from the order of operations. So if I was to evaluate this, this would become 4 times 6, and then that's 24. But we're claiming that's the same as over here. 4 times 2 is 8. I had to do what's in the parentheses first, right? But 8 times 3 is also 24. So what we see is that the moving what was grouped together did not change the answer with multiplication. Do you remember what we said was group? That's the associative property. So I'm going to call this the associative property. I'm just going to abbreviate here. And instead of writing out multiplication, I'll just put the star 4 times. Okay. Next, example C. 4 plus 10. Okay, so that's 14. And I'm claiming that's equal to 2 times 2 plus 5. Well, 2 plus 5 is definitely 7. And 2 times 7 is also 14. So these two things are equal. Just wanted to check that first. But let's see if we can't see what how this worked out. How is this done? Well, if we took the 2 and we're going to multiply it to the sum of 2 and 5, but if we multiply them one at a time before we add, we would get the 4 and the 10 from the other side. So this process of saying that multiplying the sum is the same as multiplying each part and then summing that is called the distributive property. And can you see that the 2 was distributed? This times 2 was distributed to each one of those. And the full name of the distributive property is the distributive property of multiplication over addition. And that one is really important to know the full name of 2, because we can only distribute multiplication over addition. We can also do it over subtraction as well. But you can't distribute everything over everything else. We'll learn that exponents can't be distributed over addition, but multiplication can. All right, I believe we have one more example here. Okay, so what we have here is something very similar to what we just did. It's just involving division. So I do think it's important to realize that you can distribute multiplication over addition, but you can also distribute division over addition. And that's because division by 3 is really the same as multiplying by 1/3. So I would say that this is really just doing this. So you can see that it is the distributive property here of multiplication, even though it's division. So I'm going to call this the distributive property of multiplication over addition. Even though it's got a division bar, I want you to start thinking of division as being related to multiplication. All right. Next, we're going to label each property as either the multiplicative inverse, the additive inverse, the multiplicative identity, or the additive identity. Okay, so again, we need to kind of talk about what these terms are, and I don't want to belabor the point too much right now. I want you to have just kind of an intuition for it. But the word inverse, oh, I have it on brush mode. The word inverse means to undo. That's what it means to invert something, to undo it. The word identity is to not change. And I think a key word for you to think of when you see identity is the word identical. If two things are identical, they didn't change. And whether it's multiplicative or additive, well, that's easy to determine based on whether or not we're using plus or times. 7 plus 0 is 7. That is the identity property of addition. And so what we're saying here is that 0 is the additive identity. And again, I don't want to go too deep into this right now. I just kind of want to build up your intuition for recognizing these properties because they are so important. But think about how many numbers are an additive identity. Hopefully you come to the conclusion that there's just one. There's just one number that when you add it, it doesn't change what you added it to. All right, let's take a look at the next one. 3 times 1 is 3. Well, that's, again, an identity. I'm saying 3 stays the same. This time we're using the multiplicative identity. And so the number 1, underline is, but what I'm trying to say is the, that's what I'm trying to emphasize. It is the multiplicative identity. There's only one of them. And as we study more and more complex algebraic structures, we're going to always be looking for that unique identity that exists for the operation that we're dealing with. All right, let's take a look at the next one. We have 1/4 times 4 is equal to 1. So can you see the kind of canceling out, the undoing? So I want you to think about this as being an inverse kind of thing. And what we see is that 4 is the multiplicative inverse of 1/4. Let me write that down. 4 is the multiplicative inverse of 1/4. Why? How do I know that? Well, when I multiply 1/4 by 4, what do I get as a result? I get the multiplicative identity. So an inverse gives you back the multiplicative identity. Well, what else could we say about this? Could we say that 1/4 is the multiplicative identity of 4? Well, I certainly can. If I just simply use the commutative property of multiplication and change the order, you can see that 1/4 is the multiplicative, inverse. I said identity earlier. It is the multiplicative inverse of 4. So I'm going to say that 4 and 1/4 are multiplicative inverses of each other. Now, what about other numbers? Is there just one multiplicative inverse, or in this case 2? No, there's not. The number 5 has the inverse of 1/5. But how many multiplicative inverses does the number 5 have? Well, we just said 1/5. Is there any other number I can multiply by? You might say 0.2, but that's the same as 1/5. So the answer is no. Every number has its own multiplicative inverse, and it only has one multiplicative inverse. And that number that's its inverse, it is an inverse for as well. So that's an interesting kind of unique relationship there. All right, we got some more. Here, I'll leave the instructions there for us. Okay, so what next? -2 plus 2 equals 0. All right, so hopefully you recognize that 0 is the additive identity, right? And these two things added together result in it. So -2 and 2 are additive inverses. They, when added together, will sum to the additive identity. And you can see how you get an additive inverse is simply the negative of the number you have. All right, -2/3 times -3/2 is 1. Well, that's because they are multiplicative inverses of each other. How do you find the multiplicative inverse of a number? It's called the reciprocal. So let's write that word down. Reciprocal. The reciprocal of a number is its multiplicative inverse. How do we find the additive inverse? The opposite. All right, 1/2 minus 1/2. Well, I'm going to say that 1/2 minus 1/2 is, to the advanced mathematician, really plus -1/2, right? So this is, again, a demonstration of additive inverses resulting in the additive identity. So remember, what do we use inverses for? To get the identity. All right, so I have some kind of plain language stuff. I'd like you to match the following plain language description to the technical name. So I'm kind of mixing the way you might think about it in your head, or maybe the way I would describe it to try and keep something simple. See if you can match it to the formal mathematics name. Pause the video, and then we will check our work together. All right, and we're back. Let's see if we can't nail these down. You can add numbers in any order you like. What property tells me that I can add numbers in any order I like? Well, talking about changing order is moving numbers around. So that's the commutative property. Maybe you just drew lines or put the little Roman numeral I, I'm not sure, but I'm going to try and kind of abbreviate and write out the property. You can rearrange the grouping symbols in a multiplication problem. The group you hang out with, that's your associates. So that's the associative property of multiplication. You can multiply numbers in any order. Changing the order is moving them around. So that is the commutative property of multiplication. You can rearrange the grouping symbols in an addition problem. The addition problem, moving the groups. Groups are your associative property. Adding 0 to any number keeps it the same. That's because 0 is the additive identity. The additive identity is the one and only number that when you add it doesn't change anything. Multiplying any number by 1 keeps the number the same. Well, that's the multiplication identity. I wrote a star, I meant an asterisk. Adding a number and its opposite is 0. So if you add a number and its opposite, you get 0, which is the additive identity. That's the additive inverse. Multiplying a number and its reciprocal gives 1. 1 is the multiplicative identity, so that's the multiplicative inverse. All right. Okay, we're going to simplify an expression now.
Here's the top search result.
Okay, we're finally ready to simplify an expression. You've been waiting for this, right? So we are going to simplify 7x plus 5x, and we're going to justify our work. Now, you might be wondering why I'm spending so much time on a problem like this, but I really want to show you how to justify your work. We're going to do this one time, okay? And then for the rest of the time in this class, we're going to skip all these steps. But I want you to see why this works. Okay, I have 7x plus 5x. I know from the distributive property, which I'm kind of using backwards, that that is x times 7 plus 5. So that, the fact that those two things are equal, I know to be true because of a property that we have already discussed. Distributive property of addition over multiplication, which says that if I have multiplication times a sum, that's the same as multiplying each part of the sum and then adding the result. You're probably more familiar with going from this bottom step to the top step, but it's also important to be able to go the other way. All right, so now I have x. I can simply add 7 and 5 now. So that's x times 12. Okay? I don't need the parentheses anymore, but I can use them to indicate multiplication. So that's, the way I would justify that is I would just say just addition. So it's not really a property, it's just the act of adding. And then finally, I'm going to rewrite this as 12 times x because of the, and I could have put the x in any direction, but I put it out in front, so I'm going to fix it. And I'll say that that is the commutative property of multiplication. I know what you're thinking. You're thinking, please do not, why is it taking so long to say that if you have 7 x's and you have 5 x's, you add them together, you get 12 x's. I know that's the way it's taught in Algebra 1. But in Algebra 2, I want you to have seen this. I want you to understand that it's not just magic. It comes from our properties. And it is, in fact, true. But from now on, yes, you'll be able to skip from there to there. Okay? We don't have to list all these things, but that's why it works. So, I'm just summarizing here in the notes that demonstrates the concept of combining like terms. And from this point on in the class, you may combine any terms that have the same variables to the same power without justifying. One quick point that I want to show. You probably learned that like terms have to have the same exponent to the same power. So you should recognize that we cannot combine these terms here because that's x squared. And I want to point out why. If you're familiar with factoring, and if I factored out an x here, that's using the distributive property. Notice that pulling out that x doesn't help me any. And now I can't pull out another one, so I can't add these. So that's why this does not combine, because they didn't have the same power, and so I don't get this situation where they're just two numbers that I can add. All right, would you please take a moment to practice 2.4 A through F, it looks like, and then we will go over your answers. So pause the video and give it your best shot. All right, let's see how you did. So remember, we can combine like terms if they have the same variable to the same power. So I have a 5x here and a positive 10x, so that's 15x. I have a negative 2y minus 3y. That makes a negative 5y. Okay, and then we're done with that one. 4x squared minus x squared are like terms, becoming 3x squared. Negative 3x plus 2x. A negative 3 plus 2 is a negative 1. Okay, 12ab squared. Remember, we need to have the same variables, exact same exponents. So here I have a 12ab squared and a minus 1ab squared, making this 11ab squared. Then I have 4a squared b squared plus another 4a squared b squared, which is 8a squared b squareds. Okay, we also have 1ab minus 2ba. Can we combine these? Well, remember, the rules are we have to have the same variable to the same power. But they don't have to be in the same order because of our commutative property of multiplication. So absolutely I can combine them. And I'm going to put them in a more standard version of alphabetical order of the variables. But you don't have to. A, B, that's 1, minus 2 is a negative 1, A, B. All right. Got a few more here to deal with. Now we're going to need to open things up with a little bit of the distributive property, it looks like. So a negative 3, we need to make sure that the negative comes with the 3. And we distribute it to each one of those. So that becomes a negative 6. Negative 3 times a negative x becomes a positive. Two negatives multiplied together to a positive 3x. Now I have to take care of this negative, and that negative needs to be distributed to both of these. making that a negative 5x minus 1. I'll now combine like terms, and I get negative 2x minus 7. All right, on this next one, we're going to distribute the 5. So it's 15x plus 5. Then the negative 6 becomes negative 6x squared minus 12x, and then minus 5. Combine like terms, and I'll put them in the kind of traditional order of highest exponent first. So I have one x squared term, so nothing to combine there. 15 minus 12 is 3x. 5 minus 5 is 0. All right, on the next one, we need to divide each term by 2 to kind of open this up. So this becomes 8 divided by 2, 8x divided by 2 is 4x, and then 14 divided by 2 is 7, so 4x and minus 7. All right, and that's it for us today. I'd like you to close out by just thinking about this exit ticket. Why do you think the number set we are using is called the real numbers? Do you think there are some other types of numbers in the world besides real numbers? Research what those numbers might be. So have fun checking that out. All right, well, until next time, signing off.